So we know from the fundamental theorem of calculus that antiderivatives and derivatives act as inverses of one another, if we consider the chain rule and such. So it makes sense that if we know the derivative of inverse trig functions turn into functions involving division or fractions with a quotient, now we have a new set of rules for when we see those integrals of those fraction, quotient, division problems. And those antiderivatives will turn back into inverse trig functions. This one down here is highlighted with a star because it tends to be the favorite of AP writers, the integrals that turn into inverse tangent. So before we get started on this particular integration technique, let's remind ourselves all the ways that we can approach integrals in Calc 1 when geometry or drawing fails us. So we want to think, can we pull a constant out in front? In other words, can we take that constant and pull it out in front of our integral to make it look a little bit more simple? Can we split our integral into partial sums? In other words, can we make a sum of sums or even differences? Have we applied all of our pre-calculus knowledge? What if we expand a binomial? For instance, we would have something like 2x squared plus x all to the second power. So AP expects us to be able to write that as 2x squared plus x times 2x squared plus x and do all the distributing. Have we factored? Can we possibly factor something that's inside of an integral to make it a little bit more simple? Can we use division? So are we dividing by a monomial? In other words, do we have something like x squared plus 3x plus 1 all divided by one single term of monomial? Then in that case, everything gets divided by that monomial. Can we use synthetic division? Yes, we can when our divisor is linear. When we're dividing just by a linear term like x minus a. Can we use long division? Yes, long division will always work. It's just not always the most efficient method. And long division is the strategy we want to think about when we have either a top-heavy or an even-heavy function. Can we use trig identities? In other words, do we recognize that tangent is equal to sine over cosine, or sine squared plus cosine squared equals 1, things like that. Another question we want to ask ourselves is, does my integral have a function inside of a function? And does my integral have a function whose derivative is also present? If you can say yes to one or both of these, we want to consider u sub before we integrate. Does my integral have an exponential? Does the variable in the exponent match the variable of integration? Oops, my pen's going a little wonky. And if that's the case, if we can answer yes to these, then we want to say we want to use u sub where u is the exponent. We can also ask ourselves, does my integral after applying a u sub turn into a natural log? In other words, am I integrating 1 over u du, also known as u to the negative 1 power du? This is the one place on the number line where the power rule doesn't work, where the exponent is negative 1. And these will turn into the natural log of the absolute value of u plus c. And the last question that applies to today's lesson is, does my integral have two perfect squares? One is a constant, and one is a variable, where the constant is the a squared, and the variable is the u squared. That's when we know that our integral will turn into an inverse trig function. So in order to approach a problem like number 1, we want to look at all of these questions that we just came up with and see if we can answer any of them. Can a constant be pulled out in front? Can we split this up into partial sums, etc.? And what we're noticing is that this integral has 2 perfect squares. One is a constant and one is a variable. So the constant is 16. So a squared equals 16, which means a, the constant, is 4. And our variable is u squared, which equals x squared, which tells us that u by itself is x, and the derivative of u is just dx. So we can start to substitute our form here. So this turns into 1 over a squared plus u squared, and then the dx and the du swap out, and we have the form of 1 over a squared plus u squared du. So if I look over at my little chart here, I see that that looks like the form on the 3rd row here that will turn into an antiderivative with an inverse tangent. So that's going to turn into 1 over a, which in our case is 1 over 4, times the inverse tangent, or the arctangent, of u over a, u being x, and a, again, being 4, plus c. So for example 2, again, I want to see if I can answer any of these integral questions that we've asked ourselves. Can a constant be pulled out in front? Can I factor? Does my integral have a function inside of a function? Etc. And I see that the only one that I can confidently answer is that my integral does, again, have 2 perfect squares, one a constant and one a variable. So if my constant is a equals 3, again, because a squared equals 9, and my variable u is 2x, because u squared is 4x squared, then I can see that I have the form of 1 over the square root of a squared minus u squared. Now let's go back up to our u. If u is 2x, then du has to be 2dx. And in order to account for that coefficient of 2, I have to multiply my integral by 1/2 before I can do a switch from dx to du. So I see that this integral generally has the look and the form of this one on the first row here, which will turn into an antiderivative of an inverse sine function. So this 1/2 gets carried down in front, and I end up with 1/2 times the inverse sine, or the arc sine, of u, which is 2x, over a, which is 3 plus c. So go ahead and pause your video. Work on numbers 3, 4, and 5 by yourself. And when you're done working on them, unpause and check your answers with mine. Go ahead and pause. So for number 3, I identified a as 5 and u as 3x. And again, this integral has 2 perfect squares, one a constant and one a variable. So I'm thinking it's going to yield an antiderivative with inverse trig. And it looks just like the form that will yield an antiderivative with arctangent. So that the blue 1/3 comes down from the exchange of du to dx. The 1/5 comes down from the 1 over a. And I'm left with 1/15 arctangent of 3x over 5 plus c. Now, for number 4, whoops, let's see if I can get this. I see that I have an a of 6 and a u of x, so my du is a direct exchange with dx, And I'm in the form that will yield an antiderivative with an inverse secant function. So I end up with 1 over 6 times the arcsecant of the absolute value of x over 6 plus c. I hope that in number 5, you all notice that I don't have just two perfect squares, one a constant and one a variable. I actually have a top-heavy function. And long division will work. It's just not the most efficient way to solve number 5. So I noticed that x to the 4th minus 1 is actually the difference of two squares. And I factored it into x squared minus 1 and x squared plus 1, which helps cancel out the x squared plus 1 from the numerator and denominator, and I'm simply left with the integral of x squared minus 1 dx, which just yields power rule, and I have x cubed over 3 minus x plus c. Now, how would we check all of these answers? We would take the derivatives of our answers, and we would know then that we had been doing it correctly. So for number 6, the first thing that I noticed is I have a constant that I can pull out in front as I go down my list of questions that I might ask myself on how to solve an integral. So if I pull out the 87 in front, then what I notice I'm left with is actually two perfect squares, where a is equal to 2, because a squared is 4, and u is equal to the whole expression of x plus 1, which conveniently leaves my du and dx as a direct exchange. So I can rewrite this integral as 87 still comes out in front, 1 over a squared plus u squared du. And then I notice that it is in the form that will yield an antiderivative of an inverse tangent function. So I will be left with 87 still comes out in front every time, times 1 over a, which is 1 over 2, times the arctangent of u over a, u being the quantity of x plus 1, and a being 2, plus c. And yes, 87 times 1/2 can, of course, be combined into 87 halves. Now, number 7, if I go down my list of questions, do I have a constant that can be pulled out in front? Can I split into partial sums, etc.? I'm not seeing any of these questions that I can answer yes to. So then I think to myself, can I make number 7 look like number 6? In other words, can I make it look like two perfect squares, one a constant and one a variable? Yes, I can if I complete the square. So I'm going to pull the denominator just out of the integral and write it separately. So I'm going to write the 25 kind of off to the side. Now to complete the square, I'm going to split my middle term being 8. I split it in half. I get 4, square that 4, and I get 16. So I'm going to add 16. But if I add 16, in order to keep this expression balanced, I have to then subtract 16. So x squared plus 8x plus 16 factors into the perfect square of x plus 4 squared, and 25 minus 16 is 9. So the denominator is mathematically equivalent to the quantity of x plus 4 squared plus 9. And now my integral really does look like the integral I had in number 6, where I have two perfect squares, one a constant and one a variable. So I'm left with 1 over x plus 4 squared plus 9 dx. So a, my constant, is 3, because 3 squared is 9. My variable is the quantity of x plus 4. So u equals x plus 4. du is a direct exchange with dx. And then I can see that my integral is in the form of 1 over a squared plus u squared du. And this will yield an antiderivative of